Continuing section 7.3, the work done by a gravitational force, let's look at an example of a sleigh going up a ramp. It says a sleigh is pulled along a ramp, but the sleigh starts and ends at rest. A rope pulls the 200-kilogram sleigh up a slope at an incline angle of 30 degrees through a distance d equals 20 meters. The sleigh and its contents have a total mass of 200 kilograms. The snowy slope is so slippery, we take it to be frictionless. How much work is done by each force acting on the sleigh? Right, so to take a look at this, we can note that we have a sleigh. I started trying to draw it, sketch it out. My sleigh is not very detailed, right? Sleigh that's being pulled up this ramp. We know the mass, the angle, the total displacement it goes, that it's frictionless, which is really handy. That gives us a clue about the forces. We want to find the work done by each force acting on the sleigh. So that gives us a clue that we're going to need to figure out what forces are acting on the sleigh, right? So what forces do we have? Well, I encourage you to work this out yourself. See how far you can get in solving it. At the very least, write out all the forces you can on the sleigh. So go ahead and pause the video now. All right, now trusting you did that, we can take a look at this. We have the work. It's going to go what direction? Straight down. So that is our mg. Get that over a touch. We also have tension, because the sleigh is being pulled up by some sort of rope or cable. And then we have the normal force, right? Where the normal force is going to be perpendicular to the surface. Great. So this is looking pretty good. The other thing we might label on here is our direction of displacement, and that's just going to be along the slope. All right. So anytime we're working with forces, I like to also move them to a free body diagram. This helps me to organize my thoughts. So I'm just going to recopy the forces down here. We have the tension going up the slope, the normal force perpendicular to that, and gravity pulling down with the weight of mg. So we're going to line up our axes once again with the slope, because that's the direction of motion. So I'm going to call that the positive x direction. And the normal force is in the positive y. This allows us to have two of our forces along the axes that are perpendicular to each other. And the weight force is one that we may want to break down into x and y components. But before we get there, I'll just add a little label that the angle theta does appear like so. Let's think about what tools we have to calculate work. Well, if each of these forces are constant, we know that we can calculate the work with the force times the displacement times the cosine, excuse me, got a little too excited there. It's dot product, cosine of the angle between. So let's start with normal force. Just to write it out, we don't actually know exactly what the normal force is, or maybe you do if you're well accustomed to these inclined plane problems, or you go, oh, I know the normal force is just going to be the y component of mg, which in this case is mg cosine theta, but we don't need to get into that just yet. Let's just look more generally at the normal force. So if we have, for the normal force, I'll switch to green, so we have some contrast. The work done by the normal force is going to be the normal force, whatever that is, times the displacement, which we know is 20 meters, times the cosine between the displacement and the normal force. What's the angle between the displacement and the normal force? It's 90 degrees. What's cosine of 90 degrees? cosine of 90 degrees is just 0. So this whole expression for work is 0 for the normal force. You could write this as work sub Fn, say, or work sub n. This is not net work, it's work done by the normal force. What does this mean? It means the normal force is not contributing to the motion of the sleigh going either up the ramp or down the ramp. Friction would be, because friction is opposing the motion, and the normal force could be used in the calculation of friction, but the normal force itself is not actually doing any work. Okay, well that's pretty cool. Nice to immediately rule that out. What about gravity? Because we are in the section, the work done by gravity, so it seems worth calculating. Work done by gravity is equal to mg d, where we plugged in our force of gravity, mg times d times cosine phi. Now notice with this equation, we can use the fact that it's pointed at a weird angle, and that's okay. We don't have to break it down into x and y components. We can just say, hey, the displacement is going along that positive x direction, and so I can plug in for my angle either 90 plus theta, which would be 90 plus 30, so 120, or I can even go the other way around, which would come out to 180 plus 60, or 240. And either one would work out the same way. I'm just going to do it with the 120. So m times g times d times cosine 120 degrees. And notice the m and the d and g are all things we know, so we can actually plug in numbers here. So let's take this one step further. So 200 kilograms times the times g, 9.8 meters per second squared, times the displacement now of 20 meters times cosine of 120 degrees. And notice when we take cosine of 120 degrees, that's something greater than 90, and so that will always give us a negative. That's why it doesn't matter if we use 240 or 120. Either way, it's going to be angled away from the positive direction. So this, when you put in your calculator and multiply it out, will in fact give you a negative value. And you should find it gives you about negative 1.96 times 10 to the 4. With what units? Joules, right? Can't forget that work, have to remember that work has the same units as energy, which is joules. All right, so cool. We have the work done by gravity there. We've gotten two of our forces out of the way, and the last force is just the tension. There's a catch here though. If we wanted to plug into our general work equation done by a constant force, we can figure out the angle, because the angle between the displacement and the tension is 0. They're in the same direction. We know the displacement, but how much tension force is there? But we don't actually know that here. It doesn't say if the sleigh is accelerating or if it's a constant velocity. It's a little bit unclear. So we would be stuck if that's all we had. But the problem gives us one other clue, and it just says that the sleigh starts and stops at rest, which means it's going to have non-zero acceleration in there, but at the beginning and at the very end, it's not moving. How does that help us? If it starts and stops at rest, that tells us that what's the kinetic energy at the start? 0. What's the kinetic energy at the end? Also 0. So because it starts and stops at rest, we know that the change in kinetic energy is going to be 0. Let's tilt this down a little more. And the change in kinetic energy is equal to the net work done. So if this is equal to 0, this is going to be equal to the work done by all of the other forces present. So the work done by the normal force, which we know is just 0, plus the work done by gravity, plus the work done by the tension force. So if we then go to solve this, let's see if we can get this just a touch higher. There we go. We know the work done by the normal force is 0, plus the work done by gravity is negative 1.96 times 10 to the 4 joules, plus the work done by tension. So if I add this negative work done by gravity to the other side, we get that the work done by tension is negative 1.96 times 10 to the 4, but it's a negative negative. So it comes out to positive work done by tension force, which is what we'd expect because the tension is in the same direction as the displacement versus gravity is in the opposite direction as displacement. So the tension is doing positive work. It's helping Santa's sleigh get up the slope, while the weight of the sleigh is doing negative work. It is indeed slowing it down, fighting that motion. And that is shown in the figure. If we go back to that for a moment, we have a nice synopsis here with all the forces. There we go. That the tension is doing positive work versus the force of gravity is doing negative work. And you could incidentally do this calculation with just the component of the force of gravity that's along the x-axis. You just, in that case, would use cosine of 180, because now you're just using the part of the force of gravity that's doing negative work. So if in doubt, you should try it out and check that it does in fact work. I dare you to. Right? This wraps up section 7.3, the work done by the gravitational force.